Welcome to the class of complex analysis. So in this section we are dealing with the maximum modulus principles. So the first version of maximum modulus principles is that suppose we have a region G. We have a region G and this region means it is an open connected set. Open plus connected, that means it is region. Open connected set, and f is a function from G to C and f is analytic. And suppose you consider there is a point A in G such that f of a modulus of f of a is greater than or equal to modulus of f of z for every z in G. If you take any z in G such that modulus of f of a is greater than or equal to fz, that means f of a is the maximum of fz. Or I can say that mod f attains its maximum at the point A. Then f must be constant. Suppose f analytic function defined in an open connected set G which attains its maximum on that set G, then that function should be constant. This is the meaning of first version. Actually we already proved this first version or maximum modulus principle in zeros of analytic function section. Okay, so there we proved this theorem by means of Cauchy's integral formula. Here we have a alternative proof. Okay. Proof. So I consider let f from G to C be analytic and take omega equal to f of G, the range. Okay, and let A is a point in G such that f of A is greater than or equal to mod fz for every z in G. This was our major assumption. Since A is a point in G, we can say that f of A is an element in omega. So take alpha equal to f of A. Then alpha is an element in omega. Ready. Now we want to prove that f is a constant function if function has this property. To prove f is constant, we assume suppose f is not constant. If f is non-constant, what will happen? If f is non-constant, if you assume f is a non-constant function, then f is a non-constant analytic function defined in an open set. Then f is a non-constant analytic function. Non-constant analytic function defined in an open set G. We know that we have open mapping theorem. Open mapping theorem says that when we have a non-constant analytic function, then that function should be open, which means which maps open sets into open sets. Non-constant analytic function is open map, is open, which is the statement of open mapping theorem and which is defined on an open set. Therefore by this open mapping theorem, and here if you assume that f is a non-constant function, it will be non-constant analytic. Therefore f from G to C is open, is an open map. So which maps open sets into open sets. Since G is open, f of G should be open. What is f of G? F of G means omega. Omega is open. Okay, now we have alpha is a point in omega. Since omega is an open set and alpha is a point in omega, alpha should be an interior point of omega. So which implies alpha belongs to omega is an interior point. So by definition of interior point, we can consider a radius such that a neighborhood with that radius is fully contained in that set. So which implies there exists some epsilon greater than 0 such that B alpha epsilon, the neighborhood centered at alpha and radius epsilon is fully contained in omega. Okay. Now let Z is a point in B alpha epsilon. So which means that Z is a point in B alpha epsilon means what is B alpha epsilon, which is contained in omega. And what is omega? Omega is nothing but f of g, right? F of g, yeah, f of g. So Z is a point in f of g. Okay, so when Z is a point in f of g, Z can be written some so for that I will consider a point w here, so some beta here. So for the notation, I take beta belongs to b alpha epsilon, therefore beta belongs to f of g. Then beta can be written f of z, where z is a point in g. Okay. For convenience, I take beta is an element in b alpha epsilon, then beta belongs to f of g, because b alpha epsilon is contained in omega and omega equal to f of g. Therefore, beta is contained in f of g. Therefore, beta can be written f of z, where z is an element in g. Right. Okay. So, what can you say about this? Consider b alpha epsilon. What is b alpha epsilon? Alpha equal to f of a. Since f is a mapping from g to c, this alpha is a point in the complex plane. Okay, alpha is a point in the complex plane. Suppose this is our alpha. Then consider b alpha epsilon. What is b alpha epsilon? That is a neighborhood of alpha with the radius epsilon. Okay. Then since you can consider since alpha is a point in complex number, what is this distance? With this distance is actually mod alpha. Mod alpha. If Z is any point in the complex plane, then distance from the origin to that point is actually called mod Z. So since alpha is a point here, distance between the origin and that alpha will be actually mod alpha. So this is our mod alpha. Okay. Okay. Then if you consider any point from this region, okay, then that number have the modulus value which is greater than mod alpha, right? If you consider any complex number in this neighborhood be alpha epsilon, such that if you consider any beta here, then what is mod beta? Mod beta is the distance from the origin to beta. So what is mod beta? Clearly you can say that mod beta is greater than mod alpha, because this is the distance mod alpha and which is the distance mod beta. So there are elements in this neighborhood with the property that mod beta is greater than or equal to mod alpha. We can consider such kind of elements here. So if you take beta in b alpha epsilon, there are some points beta with this property, right? Therefore this beta may have this property. If it's not, we can consider such kind of beta. Okay, so since if take a point beta in b alpha epsilon, then beta can be written f of z or z in g, and I can write here mod beta will be greater than or equal to mod alpha. We can consider such kind of beta. So I take, let beta a point b alpha epsilon such that mod beta is greater than or equal to mod alpha. I consider such an element beta. Okay. Then we have beta equal to fz, and z is mod beta is greater than or equal to mod alpha. So which means that what is beta? Mod fz. Beta is fz, and we have mod beta is greater than or equal to mod alpha. So which means that mod fz is greater than or equal to alpha. And what is this alpha? Mod alpha. And what is this alpha? F of a. So we get now there is a point in the neighborhood of alpha or f of a, that is beta, which have the property that mod beta greater than or equal to alpha. That means by getting this beta, we can choose a number z in G such that mod fz is greater than or equal to mod f of a. So which means that mod f of z is greater than or equal to mod f of a for some z in G. Z in G. So what is this? Is it possible? No, because our function f has the property that mod f of a is greater than or equal to mod f z for every z in G. Now we get a point z in G such that which is greater than that mod f of a. It is not possible because f of a mod f of a is the maximum of f of z for every z in G. So which is a contradiction. Which is a contradiction. Therefore f should be constant. F should be a constant function. So this is the first version of maximum modulus principle or maximum modulus theorem. That is, every analytic function in a region, near region G, region means open connected set, region G, and if there is a point A in G with the property that mod f of a is greater than or equal to mod f z, then it is constant. So analytic function defined in a region with maximum value means it is constant. Okay. And in this first version of maximum modulus principle, our open set G must be a region. And this I can say that this maximum modulus principle first version may not be true for any arbitrary open sets. Maximum modulus principle first version may not be true for, may not be hold for any arbitrary open set. Any arbitrary open set. That means it should be our domain G should be region. That means open connected set. For example, consider the set G equal to some G1 union G2, where G1 is defined by set of all sets such that mod set less than or equal to 1. Okay. That means the mod set less than or equal to 1 means this circle with the interior and boundary. So this shaded portion will be with the boundary will be the mod set less than or equal to 1, and G2 equal to set of all set is such that mod z minus 3 less than or equal to 1. So what is mod? This is 1 unit, 2 unit, 3 unit. So 3 is the center, 1 is the radius. Okay, 3 is the center, 1 is the radius. So this will be our mod z minus 3 less than or equal to 1. So this is the second region. I mean second set G2. This is G1 and this is G2. Their union is defined by our G. Okay. So clearly you can see that G1 is open. G1 union G2. Okay. Then G1 is actually mod set less than or equal to 1. If you consider mod set strictly less than 1, that will be open, right? Strictly less than 1. So it is only shaded region, not the boundary. Okay. Then G1 and G2 are open. Then we know that union of two open sets is open, therefore G is open. Since G1 and G2 are open, because they are the only interior open, then G is open. But clearly they are not, G1 is connected, G2 is connected, but their union is not connected. But not connected. But that means it is not a region, it is only an open set. Okay. Then define a function fz is equal to, I define a piecewise defined function z for, if z is an element in G1, and any constant value I take some 5 for if z is an element in G2. Okay. Then f is an analytic function. Now consider mod fz. What is mod fz? Mod fz has two values, mod z when z in G1 and mod phi when z in G2. That is, mod fz has two values. It is mod z on G1 and phi on G2. So what is G1? G1 is mod z less than 1, right? So in that region the maximum value will be 1 only. Therefore in G2 mod phi means 5 is the maximum value. Therefore mod fz is equal to 5 will be true for every z in G. Okay, and this phi can be written some modulus of mod phi, or which is equal to modulus of some f of a where a in G2. So what you get now is modulus of fz is equal to modulus of f of a. That means f attains its maximum f attains its maximum in G, because it attains its maximum value at some point A in G. Okay. Also I can say that f attains its maximum at every point of G2. Also f attains its maximum, because if you take any point in G2, its value is 5 and 5 is the maximum value for that function also. So f attains its maximum value 5 at every point of G2. At every point of G2, which is a subset of G. So what we have now is f set is an analytic function which is defined on an open set, which means f is analytic on an open set, in an open set G with the maximum value. So if a function which is analytic defined in an open set and it attains its maximum value, then by maximum modulus principle says that function should be constant. But here we can say that this function is not a constant function, because in G2 it is a constant value, but in G1 it is identity function. So it is not a constant function, but f is not a constant function. That means maximum modulus theorem fails here. Constant function. That is maximum modulus principle. First version fails here. First version fails. Only because of G is not connected. G is open but not connected here. So therefore I can say that connectedness of the domain is an essential criteria for this first version. Connectedness is essential. Essential for first version. So without connectedness, this function cannot be constant function even though it attains maximum and analytic. Okay, next we move to this second version of maximum modulus theorem. So second version says that suppose when G is a bounded open set, not a region, it is a bounded open set. Okay. And suppose f is continuous function on G closure and which is analytic in G. Then maximum of mod f set in G closure will be same as maximum of mod f set when set in del G. Dou G, where dou G denote the boundary of G. So which means the maximum value of mod f set in G closure will be same as maximum value of mod f set in boundary of G. Okay, so how will you prove this version? Proof. So let G be bounded and open. Okay, and f from G to C be analytic, and f from G closure to C is continuous. We have given that f from G closure to C is continuous. Okay. So since G closure, we know that every closure of a set is always compact, always closed. And since G is bounded, G closure is also bounded. Okay. Therefore, G closure is bounded and closed and bounded in C. Therefore, it is compact. G closure is compact in C. And f is a continuous function defined on a compact set G closure. So since G closure is compact, we know that every continuous function defined on a compact set will attain its extrema. Okay, since G closure is compact in C and f is continuous on G closure, f attains its extrema, in particular its maxima, attains its maxima on G closure, which means that is there exists a point A in G closure such that f of A will be, mod f of A will be greater than or equal to mod f set for every set in G closure. So this is true for continuous function. Okay. So here note that A is a point in G closure. So A is a point in G closure means if A belongs to either A belongs to G or not belongs to G. If what happen if A belongs to G? If A is a point in G such that mod f of A greater than or equal to mod f z for every set in G closure means f attains its maxima on G because A is a point in G, right? So which means f is analytic in G, we have f is analytic in G and G is open, okay, and G is open, okay, and f has maxima in G implies f should be constant. F is constant. So if f, that means if f is a constant function, then what will happen? F of A and f z all are equal for every set in G and set in G closure. So which means that a maximum of that point f z when set in G closure will be same as maximum of the function mod f z where z is a point in G, both boundary of G, both are same. Okay. Now we consider the second case. That means if f is not a constant function. If f is not constant. If f is not a constant function. This is the second case. Then what will happen? Since f is not a constant function, then f of A not equal to f of z for any z. So that we have, there is a point A in G closure such that f of A is greater than or equal to f z. Now assume let mod alpha be equal to the maximum value of mod f z where z is a point in G closure. Okay. So I consider all z in G closure. Then what is the maximum value of mod f z, which is denoted by mod alpha? Okay. So which means that since alpha belongs to this collection of f z's, means alpha can be written some f of theta where theta is a point in theta in G closure. So alpha equal to f theta where theta is a point in G closure. Now what is this G closure? Since G is an open set, G closure is G union boundary of G. G union boundary of G. Okay. So since G is only an open set, we can't apply the theorem first modulus, maximum modulus principle first version. So in order to apply that first version, we want a non-constant analytic function with the maximum value, right? So I will consider here, let theta belongs to some G1 closure where G1 is a component of G, where G1 is a component of G. We know that every components are connected and component of open set is again open. Therefore G1 is an open set. Okay, since f is not a constant function, this function f cannot attain its maxima on the interior of G1. On the interior of G1, because by maximum modulus principle first version says that if f is a function which is analytic and which has maxima on the interior to the open region, then f must be constant. Here f is a non-constant function and f attains its maxima at the point theta, where theta is a point G closure. Therefore f cannot attain or assume its maximum value on the interior of G1. Therefore it should be attained at the boundary of G. Okay. Therefore by first version of maximum modulus principle, f should attains its maxima on boundary of G. F should attain its maxima on the boundary of G. Okay. So therefore maximum of mod f z in G will be same as maximum of mod f z in Actually set in G closure is same as set in boundary of G. When the case G is bounded open. Okay. So which is the second version theorem. Now in this theorem, the boundedness of the domain is essential. Boundedness of G is essential in the second version. In the theorem. Boundedness. What happens if boundedness is omitted for G? So for that we consider an example. Take G is equal to set of all Z is equal to x plus iy such that y is in between minus pi by 2 to pi by 2. So that means we are considering y is in between minus pi by 2 and pi by 2. Suppose this is minus pi by 2. So isn't complex plane, it is minus I pi by 2, and suppose this is the I pi by 2. Then these are the elements. Okay. So which is an infinite strip. So this is our domain G. So that the domain is not bounded, G is not bounded. Okay. Now consider the function fz is equal to e power z. So that is fz is equal to e power z means e power x plus iy. So that is e power x e power iy. So this is our fz. Okay. So what is the value of fz in the boundary? So on the boundary of G, that means dou G, fz is nothing but e power x e power y values are actually minus pi by 2 to pi by 2. So I will write plus or minus I pi by 2. So these are the maximum values or the values in the boundary of that function. So which is e power x. What is e power plus or minus I pi by 2? That is cos pi by 2 plus or minus sin pi by 2. Right? So this can be written e raised to cos e raised to I pi by 2. That can be written cos pi by 2 plus or minus I sin pi by 2. So these are the values. So which is equal to e power x. This value is plus or minus I based on the values of sine. So which is plus or minus I product. So what is this value? E power plus or minus e raised to x. I e raised to x actually. So this is the value of the function fz in the boundary. Okay. So what will be mod fz in the boundary? Mod fz is equal to modulus of plus or minus I e raised to x. So which is equal to, we know e raised to I theta equal to 1, right? Therefore e raised to plus or minus I e raised to whatever this angle, this is considered to be some theta. Therefore e raised to plus or minus I theta will be equal to 1. So the maximum value will be taken as fz can be equal to 1. So I can, which implies f assumes the value, maximum value 1 on the boundary. F assume the value 1 on the boundary of G. Okay. Therefore by the second version, actually by second version what we want, by second version we can write mod fz is also less than or equal to 1 in the interior of G. In interior of G. For every set in the interior also. Okay. Now consider the actual value of the function here. Suppose we take, let's say this is a point in real number. In real number means it is a subset of complex number. So it is also belongs to C. So when z is a real number, z equal to x plus I will become z x itself because y is 0. Therefore e raised to z will become x. Right? Okay. Therefore fz will become, what is fz? E power z. So here e power z is x. Therefore actually it is e power x. Therefore e power x. This will be the value fz when z is a real number. So what happens when x tends to infinity? When x tends to infinity, e power x will tends to infinity. That means mod fz also goes to infinity. When x tends to infinity, mod fz goes to infinity. What is x real number? Real number means the elements are belongs to this line, this x-axis or this line, and this is y equal to 0. Okay, so when you take any element in the inside our region or our bounded, our G, open set G, then its corresponding function value goes to infinity. But on the boundary, function attains the maximum value 1. Right? So which is a contradiction? If the function attains its value on the boundary, that is not equal to the maximum value of that function here, because of our function, our set G is not bounded, which is not possible, or which is a contradiction to our second version. So by second version, fz is less than or equal to 1, and this should be the maximum value of every point in set. Every point is set in G. But here, if you consider any point in the axis, that point has the value tends to infinity when set x tends to infinity. Which means second version fails here. Second version fails. So that boundedness of the domain is an essential topic or essential criteria for existence of second version. Okay.